Okay. So hello, everyone. So in this lecture and the next lecture, I'm going to talk about some efficient algorithms for random graph matching. So in fact, I should say that there are many actually very interesting algorithms developed in the recent years. So I'm actually going to focus on two examples. So one, in this lecture, I'm going to talk about this algorithm design from based on the spectral method and also from this optimization perspective. In the next lecture, I'm going to talk about this low-degree polynomial approach. So those two designs, I think so I picked those two because they are kind of principled, and then you do not need really ingenious ideas to some extent. There are already some kind of existing roadmaps for you actually to do this. But you can also apply this method to other problems, not just on the random graph matching. Okay. So let me just briefly recap of the random graph matching problem. So I think in the last lecture, I talked about this problem. Basically, it's like given two networks, like nodes and edges, and then you want to find a bijection between the vertex set of the two graphs so that after you kind of align them, then the edges are kind of maximally aligned. Or more specifically, you want to minimize the number of adjacency discrements under this particular bijection. So mathematically, you can formulate this as a combinatorial optimization problem known as quadratic assignment problem. So once again, this A is the adjacent matrix for the first graph, B is the adjacent matrix for the second graph, pi is the permutation matrix. So basically here, it's like you want to search over all the possible permuted version of B, so then maximize the inner product between A and the permuted version of B. Okay. Okay, so in the noiseless case, as we discussed last time, this reduced to a graph isomorphism problem. Okay. But as we briefly talked about last time, this problem is actually NP-hard in the worst case in general. But we still want to make some progress on this problem, especially considering these practical applications. So that's why we focus on some statistical model for this graph matching and then try to study when you can recover some hidden vertex correspondence given some correlated edge connections in these two networks. So in particular, we talk about this very simple model called correlated order-Shen graph model. Again, it's a very idealized setting. You can definitely consider more general random graph model. So let me just briefly explain this again. So basically, you can think about you have some underlying friendship network among n persons. The edge probability is p, so you have an order-Shen random graph with n nodes, and then two nodes are independently connected with probability p. And then you can imagine you're going to subsample the edges independently with probability s to obtain this first triad graph. You can think about this is the friendship network of these n persons, maybe on one digital platform, say on Facebook. So for this triad graph, it's again an order-Shen, but then the probability is slightly smaller. It's given by Q here. It's just p times s, right? And then you can think about this same set of person maybe form another friendship network on different digital platform, so you get a second graph, G2 star. And then to model the scenario, you do not know actually the true node identities. So you can think about, you can randomly shuffle the labels of the second graph according to some unknown permutation pi star, and that gives you the second graph. So then the question now is that given this G1 and G2, and you want to recover this latent node correspondence. Okay, right? Okay, so again, something important here is that this parameter s is very important, because if s equals to 1, then these two graphs are exactly the same up to some isomorphism. So this is the we call it the noiseless case. But when s is less than 1, then you will see some edge difference between G1 and G2, right? So this is kind of like, you can think about this as a noisy version of graph isomorphism problem. Okay? Make sense? Questions? Okay, good. Yes, and now in this talk, sometimes I'm going to think about not in terms of s, but in terms of 1 minus s. So I call it delta. So delta just captures roughly the fraction of edges differed in the two graphs. Okay, so a better algorithm should be able to tolerate a larger delta. Okay. Okay, so this is actually what we covered in the last lecture about information-theoretic limits. So here I focus on the exact recovery. Last time we actually talked about many different performance criterions, partial recovery, almost exact recovery. But in this lecture, I'm going to focus on exact recovery. In the next lecture, I'm going to talk about some algorithms for partial recovery. So for exact recovery, if you simplify this a little bit, focusing on this p is a little 1, then this threshold has this very nice form given by n times p s squared minus log n go to infinity. So once again, this np s squared is the average degree of the so-called intersection graph. Right? So the intersection graph, once again, is the graph contains all the edges in both A and B, like in these two graphs. So that's why you have the edge probabilities like p times s squared, because you subsample the edge independently twice. Okay, and then once this go to infinity, you know the intersection graph is connected. So this threshold is actually coincide with the connectivity threshold, at least in this p equal to little 1 region. Okay, so now let's think about computationally. So that's the main focus of this lecture. So it turns out that when s equal to 1, as I said, or delta equal to 0, so the two graphs are just exactly isomorphic to each other, this optimal condition just reduced to np minus log n go to infinity, right? So then it turns out that you can actually achieve this optimal condition in linear time using some efficient algorithms. So meaning that there are some efficient algorithms as long as np, like this average degree, np is bigger than log n, then there's efficient algorithm to actually recover this underlying permutation pi star exactly. Okay, so in fact, let me give you a little bit of the idea behind this algorithm. So in fact, in the one idea of this algorithm is based on this so-called distance sequence. So I mean, like in lots of this algorithm design, you want to come up some like a signature vector for every node. And then the hope is that this signature vector can help you to distinguish different nodes in the graph. Okay, so in this s equal to 1 case, you basically just have this Audacian random graph, right? And then you just reshuffle that, but somehow you still want to kind of re-identify the node, right? So you want to come up some feature vector, some signature vector for this node. So one signature vector is called the distance sequence. It's basically, let me call it as a D for node I. It's just let me write in this way, the number of one-hop neighbors of I, and then the number of second hop, and then the number of third hop, and then up to roughly the number of log n over log n hop. Okay, so this give you a vector, and each coordinate is the number of neighbors of this node I of a given hop. Okay, so basically if you look at your graph, you just look at the first one, just the number of neighbors, or one-hop neighbors. The second coordinate is the number of two-hop neighbors, and so on and so forth. Okay, so roughly, if I remember correctly, the idea is the following. So now if you want to show this algorithm works, you basically want to study the case where if you look at two different nodes, I and j, and then if I and j are the same, then this di must equal to dj because there's no noise, right? But then if I and j are different nodes, you want to study what's the probability di equals dj, right? So if I does not equal to j, you want to roughly estimate what's the probability of di equal to dj. So now this becomes some interesting math problem, right? If you have this particular distance sequence, then what's the probability each of these coordinates like overlaps? So roughly the intuition is that if you look at the first guy, so that's easy, right? So the distribution here is a binomial, right? N minus 1 and then p, right? Does it make sense? Right? And now if you look at the two different nodes, I mean, if you ignore a little bit of the correlation, you should expect the first coordinate is like two independent binomials of n minus 1 comma p, roughly, right? Because if you pick a node I and j very likely they're far away, so their number of one-hop neighbors is more or less independent. So now the question becomes, if I give you two independent binomials of this parameter, what's the probability they will have the same value? Okay, so it turns out that this probability is roughly given by 1 over square root of NP. Square root of NP is I think it's a standard deviation. So let me not talk too much, but that's roughly the estimate you can get. And it turns out that you can do the same thing for the other hops. So if I remember correctly, this one is roughly to the power of L. Well, L is actually the number of hops. So in this case, it should be log n over log n. Okay. And then in this case, if you do, if NP is at least a log n, then if you do that, you can put some big constant here and then make this to be much smaller than 1 over n squared. And then you can run a last layer of union bound, because now for any two pair, the probability they coincide is 1 over n squared. You have like n squared pairs. So if this is less than 1 over n squared, then by union bound, you can show that with high probability, there's no pair I and j that you will have this di equal to dj happens. Okay, so that's roughly the ideas. Yes?
So clearly, if you have like two isolated vertices, you'll fail.
Yes, yes,
so is
that's
there a
one.
fitting time result that says if you don't have two isolated vertices, you'll succeed?
So one thing that I should say is I'm working on this condition. So NP minus log n go to infinity, so there's no isolated node. So that's why in this calculation, I don't consider the effect of isolated node. But
what I'm saying is like in the connectivity result for GMP, there's like really strong hitting time result that says as soon as you don't have an isolated vertex you're connected. It's the same hitting time if you add edges.
Yes.
So it could be that the hitting time for the algorithm to work is not having two isolated vertices.
That I'm not quite sure about that result.
But it should be true. Right?
Yeah, but I think it should be true. Agree. Because on one hand, if you have isolated nodes, then you cannot match them correctly.
Right.
But this, I think as long, this algorithm will work. Yeah. Yeah, like as long as you don't have, as soon as you don't have like the isolated nodes.
If you have one, you're okay.
Sorry?
If you have one isolated node, you're okay.
Yeah, if you have one, I think that might work, right?
That's what I'm saying.
Yeah, true. Yeah,
two.
yeah. So that's what I'm saying. Yeah, but anyway, yeah. If you want to understand, yeah, yes.
What is time here? Like optimal condition is attained in linear time. What does that mean?
Oh, time here is the complexity of the algorithm. So for example, if you want to compute this distance sequence, it's actually linear time because you basically look at the node n and then just look at try to explore the neighborhood, and then you only do up to log n or log n. So it's maybe like approximately linear time. So that's what I meant, like the time complexity I meant.
And what do you mean by optimal condition?
Is this condition. So as long as this condition holds, then this algorithm works.
But then the condition is given in the problem, right? It's independent of the algorithm, right?
Sorry, second?
The condition is, like for a given problem, either the condition is satisfied or not satisfied. It's independent of the algorithm, right? So the algorithm need not find the condition, right?
Yes. But
whenever the condition is satisfied,
yeah. Yeah,
Oh.
yeah. So that's what I meant. Like this condition holds for any algorithm.
I see.
But I think the surprising thing is that this particular algorithm actually works as long as this condition holds.
I see.
Yeah. Okay, the reason I want to talk about this is you can see that as long, if you have a little bit of noise when s is less than 1, then that idea is kind of becomes fragile in the sense that you can see that it's not that easy to make it work anymore. I mean, although you might, but at least it's not that very easy to do or very clear. Okay, so in fact, when in the noisy case, very little is known for efficient algorithm until very recently, like 5 years ago. So when we start to look at this problem, and then that was back in 2018 roughly, and then suddenly there are a lot of people actually interested about this problem, so came up some various algorithm ideas. Okay, so one algorithm or that I want to talk about in this lecture is actually based on the spectral method. Okay, so here is actually the guarantee that we can get for the spectral method. So again, P is the edge probability in this parent graph. And then delta is, you can think about, is a fraction of errors or different edges in the two graphs. And then in this paper that back in 2019, we are able to show that you can get an exact recovery using a new spectral method with high probability if the two conditions hold. The first condition basically says that the average degree has to be like polylog n. And the second condition basically says that if you look at the fraction of the default edges, it has to be like 1 over polylog n. Okay, so capital C here just sounds like a large absolute constant.
It's the same in both?
Not really. I think, yeah, but you can pick it to be same, but it's not the same from the performance. So I remember in the general form, this is like 48, this is like 8 or something. But it's not that tight, so that's why. So I don't want to show that specific constant here. Okay, but one thing is that even though this appears not that strong, but it actually already improves significantly over some classical spectral methods. So later I'm going to show you some classical spectral method, but they require delta is actually polynomially small, like n to the minus c. So it's like from log n to the minus c to n to the minus c. I mean, you can think about it's already a like exponential improvement in terms of the noise tolerance. And another nice thing about this algorithm, even though this is not a state of art for the efficient algorithm, but it actually holds for general model that I'm going to talk about later. For example, it also holds for the Gaussian version of the problem. So it actually holds for the very general correlated Wegener model. So it has this very nice universality property. So I'm going to talk more about this in the second part of this lecture. Okay, I think that's the result I want to focus on. Any questions before I further continue? Yes?
So in the statistical bound, you just care about NP squared.
Yeah.
Here you're looking at NP and S separately.
Yes. Yeah. So it actually certainly this is far away from the like information-theoretic limit, because if you look at this, say even NP is like polylog n, right? For this condition to hold, S can be even 1 over polylog n, right? Possibly. But what we are saying here is that this S has to close to 1. In fact, the delta even has to be like 1 over polylog n. So in that sense, there's a large gap between the guarantee of this to the information-theoretic limits. But it turns out that some of the part of the gap is actually fundamental. At least that's what we believe. So in the sense that there's a computational gap, so you probably cannot achieve this IT limit in polynomial time. So the best actually we can do up to now, I think, is when S is a constant.
Oh, I see.
Yeah, so that's the subject that I'm going to talk about in the next lecture. So I'm going to show you an algorithm based on low-degree polynomial that can work when S is above some small constant. Yeah, but again, it's far away from the IT limit because S even can go to 0 according to the IT limit, right? So in some sense, there's still like some very big open problem in this field, and like in the sense that what's the best you can do in polynomial time. Yeah.
One more high-level question. So in the last lecture, you talked about various conditions, right? So exact recovery is one of them, almost exact recovery is partial recovery and so on. So why is that you're focusing primarily on this? Are there results on the other ones also that you're just talking about?
Yeah. So in this lecture, I'll focus on the exact recovery, but in the next lecture, I'm going to talk about the partial recovery.
Oh.
But if you remember the threshold, I mean, they differ a little bit if you talk about partial recovery, but I think the difference is roughly on the log n factor. So the partial recovery, I think, for example, it should be NPS squared bigger than some constant. Here, for exact recovery, you need this actual log n. So if you don't care about this log n factor, then the truth threshold do not differ too much. Yeah. But anyway, I focus on the exact recovery in this lecture. I'm going to talk about the partial recovery in the next lecture. Okay. So now I want to talk about this new spectral method because, as I promised you at the very first lecture, I kind of say that in this new type of planted models, this classical way of thinking about spectral method may not immediately work, because in this problem you don't have the low rank structure. So let me now explain a little bit more. So for the spectral method, they're actually a very powerful method for estimating hidden structure by looking at the leading eigenvectors of the data matrix. So we have actually successful stories in many different planted models. So for example, this planted clique problem. So you have a large hidden clique in this large Erdős random graph, and you want to recover the location of the clique. So here, if you look at this adjacent matrix of the planted clique model, it's approximately low rank. So that's why, for example, you can look at the second largest eigenvector and use that to help you to identify the location of the hidden clique. Similar idea also applies to the stochastic block model, planted partition, clustering, graphon estimation, matrix completion, or even ranking. So somehow, as I said, the underlying structure is that often this data matrix is approximately low rank with some large eigengap. So then that's why even you have some noise, as long as the noise perturbation is smaller than eigengap, you can still look at the eigenvectors to recover the hidden structure. So here's one specific example in the community detection problem. So for example, in this case, I look at this, it's like 3 blocks. Okay, so like 3 communities. Within the community, the edge probability is P, outside is Q. Let's say P is bigger than Q. And then I can write this adjacent matrix A as its mean plus the deviation from the mean. Right. So now by writing this way, I can look at the spectrum of the adjacent matrix A. So the first thing is that I have this deviation, A minus its mean. This, after proper normalization, you can roughly think this is as kind of the Gaussian random matrix. So then that's why you have a bulk of spectrum. In particular, there's a precise characterization given by semicircle law. So it's roughly the spectrum after normalization is from -2 to 2, and then follow this particular semicircle law shape. But then you still have the mean part, right? So the mean part will contribute some large eigenvalue that is outside of the bulk. So roughly the largest eigenvalue from this mean is actually given by the size of the community times the difference of edge probability divided by the normalization. So this sigma is roughly square root of NQ in this problem. Okay? So now if you indeed have this kind of a picture, then you can use some some perturbation theory in spectral method. You can show that when the eigengap, like the gap between the largest eigenvalues here to the bulk of spectrum, yes, so it's actually much larger than the spectral norm of the perturbation. So then you can show that the leading eigenvectors of A are actually very close to the leading eigenvector of the mean. And then if you know the eigenvector of the mean, then you can immediately recover the communities. So that's the kind of the idea behind this spectral method for community detection. There's some other variations, like in the sparse case, this picture is not exactly true. You need to do something else. But roughly, it's fair to say that many algorithms are based on this underlying low rank structure. But one thing that we will see is that for the graph matching problem, I don't have this kind of structure anymore, because my 2 graphs are just the same graph. And then it's like you don't have the mean part, basically. The mean part is just is like completely uninformative because like P equals Q. So you don't have this. So after proper normalization, for the purely ordered Xianyi, you just have this bulk of spectrum. And you can see that the eigengap is really like vanishing in this case. So that's why you will see that in our case, if you have a little bit of noise in the problem, then if you directly look at these kind of leading eigenvectors, so they're not that informative for matching the nodes anymore. Okay, so now let me actually continue to talk about then how can we develop a spectral method for this problem. So here again, it's just some very high level, like a paradigm. If we want to design a spectral method, roughly it kind of follows this. So you do the eigenvalue decomposition for the first graph, A. So you get eigenvalues lambda I, and the ui are the eigenvectors. And you do the same eigenvalue decomposition for the second graph, B. You get a bunch of eigenvalues, mu j, and the eigenvector vj. So now, remember, we want to actually match a particular node to another node in the second graph, right? So what you can do is that you can try to construct some similarity measures between, say, node K and node L, based on their eigenvalues and eigenvectors. If you can construct this similarity matrix X, where, say, the XKL, the KL's entry, give you some very good measure of the similarity between the nodes, then in the second step, you can reduce this to a linear assignment problem. Basically, just find the permutation that maximize the sum of the similarities under this permutation. Okay. So now the challenge is that how you construct this similarity matrix, right? Based on the eigenvalues and eigenvectors. And ideally, what you want is that if K and L are the true correspondents, you want the similarity to be high. And then if K and L are fake matches, you want the similarity to be low. So then you can separate them by doing this linear assignment or even some very greedy thresholding algorithm. Okay, makes sense? Okay, so now let's talk about then what are the existing spectral methods. So one very natural idea is that if you want to construct this similarity matrix, well, what you can do is that you can take the leading eigenvector. Say in this case is U1 and V1. So those are the eigenvectors corresponding to the largest eigenvalue. And then you can just try to align them. So you can construct this X just as the outer product between U1 and then V1. The S1 here is just a sign correction because you do not know the eigenvector up to some sign flip. Okay? And then you can try to do a linear assignment based on X. Okay, so effectively the idea is the following, right? So you have two graphs. You take the leading eigenvector for the first one, take the leading eigenvector for the second one. You basically just try to sort the eigenvectors. And you know that the permutation just permutes the coordinates of the eigenvector, right? So the hope is that if this U1 and V1, they actually carry the information, after sorting the entries, that should give you the true correspondence. Okay. So you can generalize these ideas. I mean, there's no reason you want to stop at the leading eigenvector. You can look at the second, third. So you can consider them like some low-rank version of this problem. There's also another idea back in 1988 by Yumiyama. So they actually consider what we call full rank method, where they are not only aligning the leading eigenvectors, they are aligning all the eigenvectors. So Ui, Vi, I actually from 1 to n. Okay, Si here again is just some sign corrections. Okay, and then the hope is that this X give you a better similarity measure of all the pairs in the problem. But unfortunately, it turns out that all these methods work really well if there's no noise. So if there's no noise, then U1 and V1, they're just the same up to some like shuffling of the coordinates. Then these actual methods actually work very well. But as long as you inject some noise in this problem, then this method actually becomes very fragile. Okay. Again, the reason is because in our problem, these two graphs or two adjacent matrices, they are full rank and they have vanishing eigengaps. So that causes some decoloration of the eigenvectors Ui and Vi, even when the noise delta, remember delta is the fraction of default edges, is actually polynomially small. Okay. So in a sense, basically what I'm saying is that if you have some noise, Ui and Vi, they are not that correlated anymore. So here is the like one simple experiment that we did for this problem. So we start from the noiseless case. So A and B here are just purely isomorphic. And the 500 vertices, H probably is 1/2. So this is the ideal situation. There's no noise. I look at a particular eigenvector, U100 here. Okay. And then here I'm varying the index J for the eigenvector for the second graph, Vj. Okay, and then the y-axis just captures the squared inner product between U100 and Vj. Okay, so one thing that you can see that if J is equal to 100, you get a perfect correlation. So that's what we expect, right? Because this is a noiseless case, U100 should be the same as V100 if you do under the true like a vertex correspondence, right? But then the correlation to the other eigenvectors, they are like 0. Okay, so that's the ideal situation. That's why all these previous methods, like spectral method, work. But if you add a little bit of noise, you see something changes. So in this case, now my two graphs, they differ by 0.1% of edges. You can see that this U100 is still correlated with V100, but you see that U100 also correlated with some Vj for j close to 100. You can keep injecting more and more noise in this problem. You can see that the correlation between U100 and V100 decreases. And then U100 also becomes correlated with some Vj for j close to 100. Okay. So this is the picture that we have if you inject like 5% of edges. And you can see that becomes like this nice shape. Okay. Okay, so based on this simulation, somehow it suggests that for this problem, if you want to use the eigenvector for, or the eigenvalues for the graph matching, you somehow cannot just focus on aligning Vj and then Uj. You should try to explore the correlation between, in this case, U100 and Vj for j close to 100. Make sense? Okay. So that actually brings up our new method. We actually call it GRAMPA. I think Chen actually came up with this name, if I remember correctly. It's a graph matching by pairwise eigenalignment. So this is okay, one thing. So let me pass this to you. So the first important thing is that you can see that we align all pairs, I and j. Right? So in the previous cases, we only align, say, ui and vi. So the eigenvectors of the same index, right? Here we actually align ui and vj for all pairs. Okay? And now the alignment is actually also measured by the quality if you project this ui and vj onto the all-one vector. So this j here is just all-one matrix. Okay? So this is the alignment between the eigenvector part. And we also actually weighted according to the distance between the corresponding eigenvalues, lambda and μj. So it actually has this kind of funny form. So capital K here is just some like a kernel that we're going to apply on this problem. Eta is some bandwidth parameter. So basically, we're going to choose some kernel so that if lambda and μj is much smaller than eta, like this bandwidth, then we're going to assign some large weight, because we believe their corresponding eigenvector u and vj are correlated. If the eigenvalue difference is much bigger than this bandwidth eta, then we believe the correlation is already very weak. So we want to assign some small weight to this. Okay? So that's kind of the idea behind this construction. So in particular, we actually choose a particular like form of the kernel. It's actually, this is called Cauchy kernel. So it's basically looking at this lambda minus μj square. So like as I said, if lambda and μj are much smaller than eta, then this weight is roughly 1 over eta. And then eta we're going to choose to be relatively small. So you have a large weight. And if lambda and μj are large, then this is roughly only like eta. So then the weight is small. So it's difference like 1 over eta versus eta, roughly. Okay. So let me emphasize again, in our method, really the crucial thing is that all these pairs of eigenvector matter in this construction. And then we have these particular spectral ways to penalize the pairs whose eigenvalues are far apart, because we believe their corresponding eigenvectors are more decorrelated. And this particular form, more or less, is inspired by the eigenvector correlation decay in this random matrix theory. They actually have a very similar form as we show here. Okay. Yes?
Why do you have the J thing?
Yeah, so that's a good question. So the J thing, there are many ways to look at this. So let me write this here. Yeah, so another way to write So let me expand it out. So this one, if you expand it out, it's like this, right? Okay. So what does it mean is that you compute the inner product between UI and the O1 vector and the VJ and the O1 vector. Okay. So it's another measure of quality of the alignment, because if you believe UI and VJ are correlated, so they are pointing the similar direction, when you project these to O1 vector, these two should actually be large. On the other hand, if UI and VJ are more like orthogonal, if you project to a particular O1 vector, then the product will be small. So that's just another way of measure the alignment quality.
So you can just take UI inner product of VJ.
UI and the inner product of VJ. But the thing is that, you do not know the underlying permutation. So UI and the VJ, when I say they are close up to a relabeling of the coordinates, right? So if UI and VJ, even they are the same, but then there's a shuffling of the coordinates, then if you directly compute the UI and VJ inner product, this will be small, right? So that's why we projected to O1 vector. And in fact, the reason why we choose O1 vector is again because we do not know the permutation. So if you if you project to any vector, since you do not know the permutation of the coordinates of the UI, it's effectively reshuffle all this vector you want to project to. So that's why you get a O1 vector. Yeah, so that's that's the intuition behind. Yeah. Yeah. Question?
J is not the only choice.
The J is not the only choice.
Remember we tested with some, for example, AJB, which also.
Oh yes, yeah, that should work. Yeah. Another reason that I'm going to give it to you is that this form also naturally arises from some optimization problem. There you will see again at least why you have this particular form. Okay, another thing that I want to say is that if you look at this eigenvector part, if you rewrite this a little bit, so the one that I write in that form, but you can definitely write in this form. Right, just move this UI and VJ a little bit. So the good thing is that you can see that this is like the projection matrix. And this is the projection matrix. And now this projection matrix is actually invariant to the sign of the UI. So that's why in our problem, our method, so we don't even need to worry about the choice of the signs anymore. You can just directly look at this projection matrix, UI transpose. Okay. Next, I want to give you another interpretation, where at least, in fact, to be frank, this is actually not our original way of figure out this method. It turns out that we actually figure out this method through some optimization view first. So let me actually explain to you this is a different view from optimization perspective. So remember, this graph matching problem can be viewed as a quadratic assignment problem, as I said in the beginning. And now, if you think about in terms of optimization, then you can think about, okay, I have some combinatorial optimization problem, right, which is NP hard to solve, but I can try to do some convex relaxation, right? So that's just another way to think about this problem. So let me explain to you. So here, the original form is given by the inner product between A and the permuted version of B. But if I want to maximize this inner product, it's definitely equivalent to minimize the difference, right? Because the Frobenius norm of A and the permuted version of B, they're going to stay the same, right? So the only thing that matters is the cross term, the inner product, right? Okay, so the nice thing now is that if you look at this one, so this constraint means pi is like a valid permutation matrix. So the first thing is that this objective in this form is not that nice, but in fact this objective is equal to, if we multiply this by pi. Sorry, Frobenius norm. Okay. So you basically just take the Frobenius norm, just insert additional pi here. And then pi is orthogonal, so pi transpose pi is just an identity, right? So now the one nice form now is that this objective is equivalent to the Fubini's norm square between a pi and pi b. Okay. And now this a pi and pi b, if you kind of think about pi as a long vector, this objective, like this a pi minus pi b, is a linear equation of pi. You take Fubini's norm square, you get a quadratic function of pi. So the objective is already in this very nice like quadratic function. Okay. Now the only non-convex part is just this constraint, like this permutation matrix constraint. But that one we all know that there's a like very natural. It's called a doubly stochastic relaxation. Is that you just keep this objective. Now I'm going to write in terms of x, subject to x is doubly stochastic. Okay, so doubly stochastic matrix is just a convex hull of the permutation matrices. So that's what I have here. Okay, so you have this quadratic objective, and you have this doubly stochastic constraints. Basically just saying that if you look at the row sum should equal to 1, column sum should be equal to 1, and this matrix has to be non-negative. Okay, so this is actually a very popular quadratic program relaxation. People actually have used that in many applications. But something that we want to understand is that what's the theory behind that, and how this relates to the grandpa method. So it turns out that this grandpa similarity matrix A, X, is some like a solution of this, but not quite. First, we actually relax this constraint to just keep this as the total sum constraint. So this constraint just says that if I sum over all the entries of xij, this is equal to n. Okay, and then the objective here, I actually put some, it's called rich regularizer. It's just basically the eta square and then Fubini's norm of x square. Okay, it turns out that if you solve this, we call it a regularized quadratic program relaxation. The solution is the same as this grandpa similarity matrix X, up to just some scaling factor. Okay, so that's just another way of looking at this.
What's the intuition for the regularization?
Yes, so I think the intuition is that if you look at this one, you don't have this rigid regularizer in the objective. But if you relax the constraint, you somehow want to add this to make this method more robust to the noise. It's a little bit difficult to see from this form, but if you go back to this eta is the bandwidth, so the same eta. So basically, if you don't have the eta here, like if you set eta equal to, okay, this does not make sense, but if eta is really, really small, then you only look at those lambda I and mu j that are very close. But then you have the noise in the problem, right? So this lambda and mu j, they're going to perturb a little bit. So you want to choose some eta, in fact, roughly according to the noise, so then that you do not focus too much on this narrow band of like a lambda mu j. So make the method more robust to the noise perturbation. Yeah, that's my intuition on this. Yeah.
Can I add something?
Yes.
So when you go from here to here, you're changing the constraint. So instead of row sum and column sum being ones, you're changing it to total sum being n. Suppose this a and b are not there. I mean, that's a silly way of thinking. But still, suppose a and b are not there, then when I solve this problem, I still want to get something that's doubly stochastic. And this rich regularizer is essentially trying to spread out the optimum.
Correct.
So that you somehow still manage the row sum column sum constraints. So if you want to minimize this...
you mean only this part, right?
Correct, only that part. If I did not have that, I can pick any matrix where the total sum is n. But if I have that part, then it is essentially saying that my matrix should be spread out.
Yes,
and that is
exactly.
Approximately similar to row sums and column sums being ones. It's not exactly the same, but it's pushing in that direction.
Oh, okay, sure. Yeah, that I agree. So if you don't have this part, if you just want to minimize this up to this row sum constraint, then the optimal solution is given by this flat matrix, like all the entries like 1 over n.
1 over n, yeah.
So that minimizes the Fubini's norm But then, so it's actually this so-called center of this Birkhoff polytope. But then, yeah, you're right. So then, for that particular matrix, definitely will satisfy the doubly stochastic constraint. Yes.
Is there any formal relation between these two relaxations?
You mean these two?
Yeah.
It might be possible to study the values of the two optimization programs and say something. But
Okay.
here, because we are studying a Plumted model, so yeah, it's hard to say what's the relation between recovering the Plumted permutation and solving the actual optimization problem. So this link is at least not.
Yeah, so I'm going to mention that later. But for our problem, in fact, for example, we actually have the guarantee proved for this regularized quadratic regularization. That performance constraint do not automatically carry over to this one. Just because the solution of these two still can be quite different. But you may be able to say in terms of objective function that you might be able to say something. Yeah, but here, since they are not exactly the same objective functions, so I don't know, but there may be something you could say. But one thing is that it's indeed like a more relaxed version to some extent, because you basically throw away a lot of constraint in the doubly stochastic matrix. And so in that sense, yeah. Okay, so let me see. Yeah, I'm just deciding whether do you guys want me to at least show some derivation to see how the solution pops up? I mean, I actually prepared that, but I don't know whether this is something you guys are interested in.
The connection between this and the algorithm?
Yeah, no, and then this ground path similarity matrix.
Yeah.
I'm not sure this will helpful for you guys to know a little bit more. But maybe I'll do that, and then we're gonna stop and have a break. Okay, so we have this objective, right? So let's say I want to verify, like solve this optimization problem, and then my hope is that this will give me back this ground path similarity matrix, right? So how to do that? Well, I'm going to use this Lagrangian form. So I'm going to copy this first, this objective function. Okay, and then I'm going to put this constraint into my objective as a regularizer. So this gamma is actually the dual variable. So let me actually write in this form. So this is just the sum of all the entries of x, and then it's equal to n. So that's my constraint, right? So I'm going to put it in my objective. Okay, and then I can just try to differentiate this Lagrangian and then try to find the optimal solution, right? Okay, so one thing is very useful. Actually, I cannot remember every time, but there's some very nice way to write this AX as the vector vectorization of X. So the vect just means that I'm going to take my matrix, look at the columns by columns, expand it out as a long vector. Okay, so then this vector of AX, it turns out that it's given by I coronet with A. Okay, this is just some algebra, but it's useful in this setting. When you have the vectorization of XB, you have this funny form of B coronet with A, and then vector with X. Okay, so the reason why I'm doing this is because now I can rewrite this Fabulous norm as some quadratic form, like a vector of X transpose times vector of X. Okay, so now I can plug in this. You do a little bit of algebra. I'm not going to repeat it here. In the side, you will get I coronet with A squared plus B squared coronet with I minus 2B coronet with A, and then vector of X. So you can see that that's indeed a quadratic function of this vectorization of x. Okay. So once you have this, then you can do the very simple like differentiation, right? Okay. So then is in our like familiar case, right? So if you differentiate this one, then you should get 2 times this guy. Right. And then this guy, you can also think about is the vectorized of x for the L2 norm. So that's simple. You get a 2 eta square vector of x, right? And then this one, again, is already in the form of vectorization. So it's 2 gamma vector of all one matrix. Okay. And then you set this to be equal. And then you can solve for vector of x. Okay, so I'm going to erase this. So then the vector of x should be equal to, you pull this to the right-hand side, and you combine this, so you get I coronet in square plus I minus 2b of I, and then plus eta square I inverse of vector of j. And then there's a gamma in front. Right. Yeah, so I'm just moving this to right-hand side, and then and then just take the matrix inverse. Okay, is that good? Yeah, and now the final thing here is that I want to write back to this grandpa matrix form, not grandma. Okay. So I need to actually kind of use the eigenvalue decomposition, right? So let's say I'm going to write the A as U lambda U transpose, and B as like V and V transpose, and I can plug in this, and then do some like computation. So yeah, maybe I'm not going to repeat the detailed computation here, but I check that. So let me do this way. Oops. The inverse. So because now you can do the eigenvalue decomposition of this one, so that's why when you take an inverse, you basically just take an inverse of the eigenvalues. You can keep the like eigenvectors. So that's why the reason I'm doing this. So you get a V cross U. Like this. Yeah. So that's just plugging the eigenvalue decomposition into here, and then use the coronet product relationship. You get this. Okay, I hope I didn't do it wrong. Yeah. Okay. And then the last thing is I just plug in this. Okay. So the vector of x now is given by gamma and times this. Yeah.
I'm confused with the dimension. What is the dimension of the lambda square?
Lambda square. Oh, that's just okay, good point. Let me see. Did I make a mistake here? Yeah, I think it's probably not lambda square, right? So I should do, yeah, thanks. I think the dimension, lambda coronet lambda, right? Yeah, sorry about that. This is m coronet m minus 2 lambda cross neck m. Yeah, thanks. Yeah, I think that's the correct one. Yeah, and then the last step, I'm not going to do that. Basically, you just expand it out. Here, you already see where that form comes from, because you will have like a lambda I plus mu j minus 2 lambda I mu j. So that's why you have lambda I minus mu j squared plus eta squared, like in the denominator. And then this is the eigenvector part where you're going to align them. Okay, so maybe I don't want to, yeah, maybe I'll stop here in case you have a question. Yeah.
Go ahead.
Okay, so I have a problem. So A and B should be like similar effects, right? They should be symmetric. So why this? Why in this equation you have 2 B connector with I, and in previous slides you have 2 times B connector with A instead of 2?
Oh, this is a typo. It should be A.
It should be A.
Yeah.
And why is it 2 times B connector with A instead of like 2 B instead of B connector with A minus A connector with B, because they're not.
Yeah, they're not interchangeable.
So then this expression is not symmetric, right?
Yes, but let me see. I see your point, but I think this is correct. So there's a step that I didn't really show. Where did I? Oh, okay. So you're worried about this one, right? Yeah, basically A saying A coronet B is not the same as B coronet A, which that I agree. But this guy actually come from this one. Yeah, so previously I erased that, but I write AX minus XB in the vector form as I coronet A minus B coronet I times the vector of X. And now I want to do the quadratic, so I take this matrix transpose times this. So I claim this is the same as this. So this is like, yeah, you take the transpose, it's the same. So it's basically square, I think this part. And then maybe you can see. So now is there's a formula, like if you take this, multiply this, it's like you take each of this, multiply this coronet with this, multiply this. So that's why you get I coronet A squared. And then you get B squared coronet with I. And then you worry about the quadratic, the cross term, right? The cross term, you can see that if you take this, it's like B coronet with A. And this one is the same, B coronet with A, right? So that's why you don't have that particular form, at least. I don't know if it's this. Yeah, at least it doesn't give you A coronet with, A coronet with B. Yeah.
This is, okay, I see.
But I think these A and B are really interchangeable. So it doesn't matter that too much in the sense that if you do that, then if you change that, then instead of get a 2 B coronet with A, you get a 2 A coronet with B.
Yeah, maybe it's the same.
And then, that. Yeah.
So essentially what you showed is that if you solve this optimization problem, the solution of this is the X that you showed us in grandpa.
Yes, up to some scaling. Like there's some scaling here, but it doesn't matter.
Okay,
yeah.
So then my question is, but to actually solve the problem, you have to round this X to a permutation matrix.
Yeah, so that's the next step.
That's what you're doing with the linear assignment.
Yes, yeah.
Yeah, can you explain how that is a good rounding? Why solving the linear assignment with this X is a good rounding?
Yeah, so that's something I'm going to do actually next after the break.
Oh, okay.
But basically, it's like we're going to show this X has a very desired form. We call it diagonal dominance. Once you have that desired form, you do this linear assignment, it will succeed. But I haven't talked about that part.
Got it.
Yeah, but maybe we can talk about after the break.
Okay.
Yeah.
So before the launch, let me set the record correct. So it was our co-author Zhou Fan who invented the name. In June 2019, we had a naming contest for our algorithm. The other competitors were Guan Pi E for eigenalignment, and also eigenmatch, expected line. Okay, and the most boring one is Gmat for eigenmatching by aligning eigenpairs. So obviously, Grandpa won the competition.
So you're saying you want to discern any credit about that name?
Without the name.
Thanks. Okay, yeah, let's have a 10 or 15 minutes break and come back for the second part. Let me resume recording. Okay.
You didn't even make the assessment.
Okay, so in the second part, I'm going to talk about the analysis of the grandpa and then show you at least some high-level ideas and sketches why grandpa works. Okay, so the first thing, I mean, we actually spent quite a bit of time on this project, try to analyze either from regularized quadratic program relaxation perspective or from the spectral perspective. So let me tell you a little bit of the story behind. So the first idea that came out of mind is that, well, we have this nice interpretation in terms of regularized quadratic program relaxation. So can we use this view to help us to understand what the solution looks like? So usually, in this kind of situation, is that you have this ground truth permutation pi star, right? And then you solve this regularized quadratic program relaxation. Maybe the hope is that you can show this optimal solution X is indeed close to the true permutation. And then if they are indeed close, then maybe doing some rounding, like doing the linear assignment, it will give you back the true permutation pi star, right? So now to do that, at least a very kind of common approach is that we can study so-called the population version of this objective function. So this is the original regularized QP. And then I can try to look at the expected value of this objective function, right? Just thinking about like try to average out the noise in the problem. So I get this so-called population version. The only difference is that I take expectation of the randomness in A and B. Okay, so now this, after taking expectation, then this becomes like a deterministic optimization problem, right? So if I evaluate this, I can write and then I can solve this population version. And then once you understand the population version, like the solution for that, then your hope is that maybe your true one, since the objective, by showing some concentration, your real objective is close to the population version, the objective, and then the solution is close to this population solution, right? So that's at least some very common approach to do that. So for this, you can do some algebra. So here I'm going to assume the true permutation is identity. And then if A and B, I'm going to standardize that. So here just subtract the mean, divide by standard deviation, just to make this A and B looks like a Gaussian matrix with IID normal entries. So, and then you can try to evaluate this expectation. I'm not going to show you the algebra here, but basically you can indeed evaluate this, get a closed form expression, solve it. You will see that roughly the population solution is actually given by this form. It's the interpolation, or like, it's a combination, linear combination between the true permutation matrix, in this case it's just identity, and then with this flat matrix. So J is all one matrix, divided by N is just like completely all the entries are equal to 1 over N. So it's given by this linear combination. The coefficient is epsilon here. And then the epsilon, you can roughly approximate this as by, like roughly is something divided by N. Okay? So this delta, remember, is the fraction of the deferred edges. Eta is this bandwidth parameter. So you don't need to worry about this particular constant here, but scaling-wise, it's like roughly 2 divided by N. Okay, so what does that mean? That means epsilon is very small if N is large, right? So that means this part is small. The major part is actually this flat matrix part. So that's why what I say here is that this population matrix is actually not close to the true permutation matrix. It's actually close to the center of the Birkhoff polytope, like this flat matrix. And then in fact, if you remember back to Siva's earlier comment, we have this ridge regularizer, like try to add this Faubourg's norm of x squared, right? That one is like picking eta to be large, then this will make this epsilon smaller, so it even get closer to the center. right? So adding the ridge regularizers somehow is a little bit counterintuitive. It's like pushing the solution even closer to the center, right? Even though our ultimate goal is to recover pi star, but somehow it's beneficial to let the optimal solution get to the center. So then what's going on, right? So then, so that means it's probably, I mean, so the true solution that you have, even though you can show it's close to the population solution, but then this population solution itself will not be close to the true permutation, right? But the same thing also applies even you look at the tighter quadratic program with doubly stochastic constraint. So you can do the same thing, you can get the same population solution. But the nice thing here is that even though the population solution is far away from the true permutation matrix, but it actually has this very nice, what we call a diagonal dominant property. Because if you look at the diagonals, it's roughly like epsilon times identity times epsilon plus 1 minus epsilon divided by m, right? So then that's roughly like, okay, so I want to say that is the diagonals actually are still like larger than the off diagonals by this factor, as long as I choose this delta and the epsilon and the eta to be small. Okay, so eta is the bandwidth parameter I can choose, so I can choose eta to be relatively small, and then delta is this noise, right? The fraction of the deferred edges, delta will be also small. So if you look at compare the diagonal entries, you have this epsilon part. So the diagonals are still like larger than the off diagonals. Okay, so what does that mean? That means in this case, even though the population solutions are far, but if I do a projection during the linear assignment, then this still can give me back the true permutation matrix pi star. Right? So in terms of picture, it's like so my point is that I don't know if you view this as like the Burkle polytope, right? So this is your pi star, like in this case it's identity. So the solution that you have is very close to the center. Center is like O1 matrix divided by n. So maybe your solution is like here, right? So it's closer to the center, but the good thing is that since it has this diagonal dominance property, if you do a projection, project back to the permutation matrices, it still gives you the true permutation matrix, right? So that's why here, like what we are trying to show is that this not only this population solution, but actually the true solution for solving the regularized QP will also have this diagonal dominance property. If you can show that, then you can show by projection, it will give you back the true permutation matrix.
So if I just look at it from this viewpoint, there's no reason for eta to be positive, right? So
eta to be positive.
I think eta equal to 0 in this viewpoint. Why should you have regularization?
It doesn't matter because here is the eta square. So I think in terms of this, you can pick eta to be negative something.
No, I meant why should I not pick eta equal to 0?
Eta to be
positive versus negative. I meant why should it not be 0?
I see. So this doesn't capture that, I think.
I see.
Yeah, because this in terms of population solution, if you pick eta equal to 0, it still works. But the eta will be useful when you control the real solution, like and then to be close to the population solution. So that will be useful, at least in our analysis, to show this real solution is indeed a diagonal dominant. So you will see that actually. Yeah.
And one more question, just to clarify. So you said that instead of solving this problem, if I solve the original doubly stochastic relaxation, then I would get a similar form for this.
Yes, yeah, exactly. You will have the same form, but then you don't have the eta anymore, but it's still roughly, it's like 2 over n, roughly. So it's still close to the center. It's, yeah, so that's what I meant. Okay, so this is actually our simulation result. I mean, we can always simulate the solution to see how it looks like. You can see that here the true permutation is identity, so this is the heat map. So the yellow entries means like, I mean, here is the like more yellow means the values are larger. So you can see that indeed the diagonal entries have much larger values than the off-diagonal entries. This is the histogram. So this is the histogram for the off-diagonal entries. This is the histogram for this is the off-diagonal, this is the diagonal. So you can see that the diagonal entries are still much bigger than these off-diagonal entries. So you have this kind of nice separation, right? So now the analysis then just boils down to prove this diagonal dominance property. So assuming the true permutation is identity, then you basically want to show that the minimal value of the diagonal entries is still bigger than the maximum of diagonal entries. And once you can show this, then you don't even need to do linear assignment, right? You can just threshold that to get back the permutation matrix. Okay, so that's basically our goal, like how you can prove this diagonal dominance. And also back to earlier point, like we proved this guarantee for grandpa, but we cannot really extend this guarantee to the doubly stochastic relaxation. It's precisely because that even we show this grandpa similarity matrix has this property, but that doesn't mean you have a tighter relaxation, it will also have the same property. So that's why so we still cannot really prove the guarantee for the tighter doubly stochastic relaxation.
I don't understand, because in the previous slide you said that for doubly stochastic relaxation also you have the similar structure.
Exactly.
But why do you not have this property?
Yeah, because it will have, but our analysis is very tailored to this particular regularized form, so we cannot really control or like directly show if this X is a solution of the doubly stochastic relaxation. We cannot show it actually has this diagonal dominance property. And then what I want to say is that if you have a looser or like a relaxation, it has this property. That doesn't mean it immediately mean the tighter relaxation, the solution will also have the same property. Yeah, so that's what I meant. Okay, I'm actually going to skip this part because I think that's not that important. But I want to directly talk about how we actually study this. So remember at the beginning, I mentioned that this one nice feature of this grandpa method is this universality, in the sense that it's not really tailored that to this order Shen-Yi like assumption. So lots of other algorithms that we develop actually crucially utilize this order Shen-Yi assumption. But for this method, basically you just need to look at the eigenvectors, eigenvalues. So that's why it's kind of more robust or like more universal to some extent. So it turns out that our analysis actually holds for more general settings. As long as this Aij and Bij, they are independent pairs, and then after centering, it has zero mean, and the variance is 1 over n, and then the correlation is actually 1 minus delta over n. So delta is the fraction of edges, default edges, okay? I should say that there should have some assumptions on a higher moments of Aij and Bij, but I'm not showing here, but you will have some other assumptions on like how the higher moments should grow. But as long as these higher moments grow nicely, then all the analysis will go through. Okay, so I'm going to focus on this more general setting, and then I'm going to tell you how we can prove that. So the key proof technique that we use is the so-called resolvent. We also use some more advanced theory called local loss. So let me actually briefly explain to you the setup first. So the resolvent is actually defined as a complex valued matrix inverse. Okay, so Z here could be it's a complex values. You take A minus Z times identity, you take an inverse. Okay, so that's the definition of the resolvent. You can plug in the eigenvalue decomposition of A. You can write this as this form. So you have this UI transpose, and then you take the inverse here. So that's why the eigenvalues part, you get a 1 over lambda I minus Z. Right? Okay, so this resolvent is actually very useful. So remember, previously I mentioned about this Wegener's semicircle density, like this kind of half circle shape. So the precise form is given by this. So I denote this by rho x. So it's like between -2 and 2. You can also define this so-called Steele's transform. Okay, so it's given by this, where you integral against the Wegener's semicircle density rho x. Okay. And now the crucial thing is that, for example, the random matrix theory shows that if you look at the empirical eigenvalue distribution of this matrix A, it should converge to this Wegener semicircle density. It turns out that one way to prove this is that you can directly try to show the trace of the resolvent normalized by n actually goes to mz. Okay, why is that? Because if you look at, yeah, maybe I'll write there. Yeah, so if you take the trace of the resolvent, so using this eigenvalue decomposition form, you take the trace of ui transpose, that's just 1, right? So in other words, what I'm saying is that you plug in this so then you take the trace of ui transpose, that's just 1, so that's why you end up with this. Right? So that is like if you write as integral form, this is like, you can think about in the following way, right? So this is the empirical distribution of the eigenvalues, right? So if you can show this quantity converge to mz, then this will imply that the empirical density also converge to the semicircle density, right? So that's actually one way that you can prove this convergence using this resolvent. It turns out that we can say much more about this resolvent. It turns out that not only we can say about convergence of the trace, we can actually also bound concentration or like the difference entry-wise. Okay, so it turns out that roughly speaking, what we know is that this resolvent should be close to mz times identity entry-wise. Okay, so if you look at ij's entry, so if I equals to j, so the diagonal part should be roughly equal to mz, and the off-diagonal part should be roughly equal to 0. Okay, so there's more precise, like error bound on this approximation, but at high level, these local laws shows that this resolvent will be close to this mz times identity entry-wise. Similarly, you can also try to bound some other property of this resolvent. For example, you can look at a particular row and look at the row sum. So you can also show the row sum is actually not that large. It's bounded by polylog n. I mean, if you take the row sum of this part, like mz identity, they should get mz roughly. But here is a little bit looser. It's saying the row sum should be upper bounded by polylog n. If you look at the sum of all the entries, you should get the diagonal part. So that's n times mz. You can make this approximation more precise. They all hold with high probability up to some like, the error part, maybe you will have some log factors. But that's, something that you can show using these local laws. So we're actually going to use this to analyze the grandpa method. Okay. Any questions? Yes?
So the A is the adjacency matrix?
Yes, that's right. So, but it's after proper normalization. So if you have a adjacent matrix, you can subtract the mean. So make the entries like 0 mean and then divide by the standard deviation. So it's a standardized version. Or here, A is even Gaussian matrix. So that's an even simpler case. But it can be more general, as you can see. Right. Good. Question?
So entry-wise bound, is that like some sort of uniformly over IG or something?
Yes, I think they actually proved that. For uniformly for all ij, they can even prove uniformly over z for z in certain range, if I remember correctly. Yeah. Yeah, it's actually a pretty strong statement. Yeah. Okay, so now the question is that how can we use this resolvent tool to actually study this grandpa matrix? So I should admit that this we actually got this idea actually by talking to Joe Fan. So he's an expert on this random matrix theory. So I should say that this view is actually eye-opening to us. But so let me actually show you like how we can use this resolvent to study this grandpa similarity matrix. So the starting point is actually this so-called resolvent representation. So remember, this is actually our expression for the grandpa similarity matrix, right? Somehow we can actually write this in terms of some like contour integral of the resolvent. Okay. So in particular, So this RAZ is a resolvent for A, and then this is a resolvent for B. This 1, transpose coming from this part. And then you take a contour integral over gamma, and this is actually the contour that we're looking at. So it's actually, so you can see that this contour actually encloses all the lambda i's, at least with high probability, because if you look at A after normalization, all the eigenvalues should be between -2 and 2, right? So we actually deliberately pick this contour to enclose all the eigenvalues of lambda I, but we do not include all the eigenvalues like mu1 minus I times eta, because they are like in this part. Okay, so that's actually crucial for this lemma to hold. So next I want to actually show you actually at least the key steps, like how we can prove this. Okay. But any questions before this statement? Like you want me to clarify a little bit? Yeah, and also at a high level, once you have this resolvent representation, then you can possibly try to study the entries of X by relating to the resolvent property. So that's why this representation is very useful. Because otherwise it's very complicated. You have to study the UI, VJ individually. I mean, for Gaussian, we actually have a pretty good understanding, so we can do that in the Gaussian setting. But for like auto Chien-Yi, it's actually much more complicated to study from this directly this one. Okay, so let me actually at least show you the proof of this lemma. So let me actually first write down this ground plus similarity matrix part. So let me actually first kind of pull out the sum of on I, and then put the sum of J inside. So there's O1 matrix, eta Vj transpose, lambda I minus mu J square plus eta square, right? So let's first focus on this part. Okay. So it turns out that this part is actually equal to, so this notation means image of this resolvent of B lambda I plus, very sorry for the notation, but this I really means the like imaginary part. Okay, eta.
So that is the imaginary component of this? The IM stands for the imaginary component?
IM, yes.
Okay.
Like IM is the imaginary complement, and this I means the like this I in the in imaginary. Okay, so let me first show you why this is true. So this is just plugging in the definition. Okay, so if you plug in the definition, the RB, so if you remember, that's the sum of J, and I should plug in the eigenvalues mu J minus this guy. So it's a lambda I plus I, sorry, this I, eta Vj transpose, right? And then these are all reals, right? So the only complex part is this. So I can take the imaginary part inside this. So this really means I. Right. Okay, now I can try to evaluate this, right? So the technique is that I can multiply both both parts by mu J plus, mu J lambda minus lambda I plus I, this I means this, eta. And then here should be mu J minus lambda I square, and then minus I, so it should be eta square. Right. And then sum over J, and then Vj transpose. Okay, so what I'm doing is that I'm just taking this, multiply both numerator and denominator by this quantity, and then the denominator will have mu J minus lambda I square minus this imaginary part square times eta square. So then I get a plus eta square. Right. Make sense? So now I'm taking the imaginary part, right? So I'm taking this part. So this I don't care, right? So then this last step is just taking imaginary part, so I should get eta, and then mu j minus lambda I square plus eta square vj transpose. So that's exactly this part that I'm writing here. Make sense? So that's just a simple calculation to show that you can rewrite this as an imaginary part of the resolvent at this particular point. Okay, is that good? And now, once I have that, then I can plug in this to here, right? Okay, so now I can rewrite this as the sum of I, ui transpose j, and then imaginary part. So let me put this outside. From RB lambda I plus I eta. Okay. Yeah, and then the next thing is that I want to write this as a contour integral, so I need to introduce the contour integral, right? So how to do that? It turns out that I'm going to treat this as a whole. I'm going to define a function fz that is defined as j r b z plus I eta. Okay. Okay, so now the crucial thing is that if I look at fz, so that's this part, there's a claim fz is actually analytic over the region as long as this z, the imaginary part, is bigger than minus eta. Okay, because this will make sure that I won't actually have like the imaginary part will cancel this. So in particular, this part will be analytic in this entire region enclosed by this contour, because look at eta 2 over. So this is the reason why I pick eta over 2 minus eta over 2 here. Okay, and then because of this, then I can use the contour integral. Basically, I'm saying, so this is from the Cauchy integral formula. So minus half to I integral of the contour fz lambda I minus z dz should be f lambda I. Okay, so this actually comes from the contour integral form. The reason is that my contour actually enclose all the these eigenvalues lambda 1 to lambda I. So those eigenvalues are like the holes, right? So then that's why you have this contour integral. You get the f lambda I. Okay, and now if you look at the f lambda I, so that's exactly the one that we have here, right? If you plug in z equal to lambda I, you get a j resolvent lambda I plus I eta. So I can now plug in this to here. So I can get a contour integral at least, right? Does it make sense? Okay. So let's actually plug in this. So now the x will become the imaginary part, sum of I, ui transpose, and times f lambda I. So this is this. So I can minus 2 pi. So this is really like imaginary part. Contour integral fz. Fz is just the j rb z plus eta divided by lambda I minus z, and then dz. Right. Make sense? So basically, I just plug in this, and then I just need to rearrange the term. So you can see that I already have sum of I, ui transpose, and then lambda I minus z, right? So I can pull everything out. So there's a like imaginary part here. So if I take this, it's like I'm taking the minus 1 over 2 pi, the real part, right? And then I can pull out my contour integral first, And then within that, you have summation I, ui transpose, lambda minus z, and you have j, rb, z plus I eta, and then dz, right? Yeah, and then we're already done, right? Because now this part is just the RAZ, right? Okay. Oh, yeah, I think I should not have a minus sign here because I should write this as yeah, you know what I'm saying. Yeah. Yeah. Okay. Yeah, so that's basically how we prove this contour integral representation. Okay, any question? Sounds good? At least the high-level idea is like this. Okay, so that's the first step. Now, as I said, in the second step, once you have this nice contour resolvent representation, then you can try to plug in the local laws for the resolvents. So let's see. So let's actually first look at the diagonal entry, like x11. Okay, so this, remember the true permutation is identity. So I want to show x11 is large, basically. So I can use the contour integral representation and then plug in this 1-1 matrix. So that is like taking the E1 transpose times E1, right? Okay, so one thing very crucial is that I kind of highlight here. I can rewrite this as two parts. This you can think about this as a row sum of the first row of the resolvent A. This is the row sum of the resolvent B, right, of the first row. You may want to actually directly plug in the resolvent approximation for this one. Remember, we actually can show that the row sum of the resolvent is at most polylog n. You can plug in those, but it turns out it's not that useful because here the crucial thing is that you want to capture the correlation. So in this case, since this 1-1 entry, so this one, the first row of the resolvent A should be correlated with the first row sum of the resolvent B. So you want to capture the correlation first, and then that's the hope that you can show x11 to be large. So how can we do that? So this is actually the key kind of idea behind this. It's actually related to this so-called leave one out relation. So I can write A in this block form. So this is the first entry of A. This is the first row except this first entry, and this first column except this first entry, and then this is like the n-1 times n-1 submatrix. I can write my resolvent also in the similar form, like this block decomposition. This is the first entry, this is the first row except the first entry, and so on and so forth. Then I can use the so-called Schur complement formula. I can try to write the first row of this resolvent A using this Schur complement formula. Okay, so here it's basically, there's some like algebra, but basically just plugging the formula. So this part should be equal to minus the first entry of the resolvent times the first row A1 transpose and times the inverse of this submatrix. Okay, so here how I get this is just plugging in this Schur complement formula. Okay. Okay, so now once you did that, then the good thing is that this part is just a resolvent, but now for a smaller submatrix, like n-1 times n-1 submatrix. So I can call this the resolvent of A superscript 1. Okay, so I have this, here they're all exact equality. Okay, so why I'm doing that is because I want to separate the randomness of this part and then this submatrix part. Okay, now I can use my local laws. So the local law says that the diagonal entries should be close to mz times identity. So in particular, this one should be close to mz. So I can approximate this by mz and then times this one. Okay, so this approximation, you can make it more precise, but this is roughly the intuition. Okay, so now you have this expression for the first row of this resolvent A. And then you can try to take the row sum, right? So take the row sum is like a hit this E1 transpose. So like take the sum of all these entries. So you should get yeah, let me actually write over there. It's a little bit jump here. Yes.
Are we currently working with the population matrix or like the actual matrix?
This is the actual matrix.
The actual matrix.
Yeah,
Okay.
yeah. So like A and B are both random.
Okay.
Yeah, yeah. But that's a good point. So what I'm saying is that you have this representation. Then what is the first row's sum? Right. So the row sum you should have the first entry like RA11, but that's like roughly MZ, right? And then the second entry is here, right? So it's basically like take the sum of this one, right? So you should MZ A1 transpose RA1Z times R1, right? Basically this is. Yes. There's some like approximation here, so I should not write equality. Okay. Make sense? Now I can plug in this, but here let me do a little bit cheating here. So let's not worry about this one, because this one we can deal with. The crucial thing is this part. Okay. So what I'm doing here in this line is that I'm ignoring this, but I'm going to plug in this into my formula. I should get an A1 transpose resolvent of a submatrix times 1, and I do the same thing for this one. Okay, and then I have this MZ plus ident. Okay, now here comes to the more crucial point. So this A1 and B1, they are correlated because they all come from this A and B, and the A and B are correlated. So A1, B1 are correlated. And they are independent of this resolvent of the submatrix. So what I can do is that I can condition on this submatrix and then average over, like study the concentration with respect to the randomness of a little a1 and a little b1. Does it make sense? So then this is how I capture the correlation, because a1, b1 now they are correlated. So at least this is the high level strategy. Okay, so that's just the way that I write this, but I would kind of pull out this A1, B1 to highlight this. And now this is the bilinear form to some extent, like A1 transpose times this big matrix times B1. So you can actually apply the standard concentration. The A1, B1 correlated, so that's why you have this 1 minus delta over M part coming from. This is coming from the concentration, like correlation, and times the trace of this big matrix. Okay. For the off diagonals, you do the similar thing. Okay, but for the off diagonals, the crucial thing here is that you still have A1, but the other one, let's say you look at the X12, then you have B2, right? So A1 and B2 now crucially they are independent, right? Because they're corresponding to the different parts of this matrix, right? So that's why if you condition this part, the mean should be 0 because A1, B1 they are uncorrelated, and then A1 already are centered. So you take expectation, you will hit 0. Right? But now here you want to study the concentration, so you can basically, it's already in the form of applying this Hansen-Wright inequality. You have this more or less the bilinear form, so the concentration part should come from this bigger matrix, the Frobenius norm. And then you pay some factor of the log of this coming from the concentration. Okay, so now the next step is to basically finish this. You need to compute the trace here, and you need to evaluate this for Frobenius norm square, or Frobenius norm here. And then the goal is that you want to show this trace part is large, I mean relatively large, and this Frobenius norm is relatively small, so then you have the separation. Okay, so here is just a little bit more calculation. So it turns out that for this diagonal entry x11, so we need to evaluate this trace. So here we're actually again using local loss, but basically is that we can plug in the trace into here, and then evaluate the trace. We get roughly this quantity here, and then this one there's no randomness anymore. It's just like a contour integral. So you can really try to evaluate the quantity, and you will get this guy here. Okay, but I kind of skipped this a little bit, but there's some calculation you need to do by plugging the local loss For the off diagonals, you do the same thing. So you want to bound this for Bayes norm. Again, there's a random part, but you're going to use the local loss to replace it by the deterministic part, and then evaluate the contour integral. So you will get this bound. So if you can show this, now you just need to style this and see how you're going to choose eta. So then this is bigger than this. Right, so that's the last part, like where we're going to determine the eta. So you want this to be smaller than this. So you do a little bit algebra, you will see that the best choice of eta is that eta has to be slightly bigger than square root of delta. And then eta also cannot be too large because you want 1 over eta to be bigger than this one. So yeah, so here is, remember delta is the fraction of errors that you can tolerate. So then this will mean that the delta cannot be too large. Sorry, cannot be too large. So delta should be smaller than like a log n to the power of -8. So that's where our condition comes from. Okay. So that's at least the high-level idea behind this diagonal dominance proof. Any questions? Yes.
So is your actual threshold sort of where you can do the union bound to get every single entry, right? Every single value entry?
You mean this condition, right?
So it is a union bound.
Yeah. But in fact, the union bound part is not really the key bottleneck. Like really, if you want to make this is bigger than this, you already needed the eta to be small.
But do you have some idea of like, imagine you could do all the analysis you wanted, when you sort of see this structure still? Like if you actually did the projection to the permutation matrices.
Yeah, that I don't see that. Yeah. You mean like you apply the linear assignment possibly will be better than just applying union bound, right?
Yeah. I mean, of course, it's much harder to analyze.
Yeah. I think that's harder to analyze because, I think that's harder to analyze. I mean, you could, but here, since we only have this like high probability bound on those entries, so it's harder. Yeah, I would say yes, exactly. Yeah, I actually don't have good control about that.
But then once you have something like this, it's inevitable that you'll get some bound on delta that is not a log.
Yeah. That's true.
Even if you, instead of doing the union bound, if you do the permutation thing, the log independence is.
Yeah. If you just start with these bounds.
Yeah, but I think
you could hope that there was something else true about
it. Yeah. So I think that's what Will is asking about. Maybe you don't need this like separation. Maybe they still have some overlap, but you hope that you can apply linear assignment to get you the true permutation. That part we actually haven't touched. Yeah. But one thing is that from simulation, we do see that the eta, they can only tolerate like 1 over like this polylog n, at least for this method. Yeah. So. Okay, there's something that you can improve this, but that's not really important. You can improve this like exponent in the log n factor a little bit in the special cases. We can also do this analysis for a tighter quadratic relaxation, where instead of putting the total sum constraint, you put the row sum constraint. Okay, so that we can still do. Yeah, but the open problem that we have, I'm going to mention later, is that if you put all the W stochastic constraints, we actually don't know how to do that using this resolvent representation technique. Even if you put the row sum and the column sum constraint, so we still don't know how to do that. So there's some like technical challenge to extend this to a tighter quadratic polymerization. Okay, I guess that's all I want to say about this. Let me just conclude that saying that in this talk, I show you this like 4-rank spectral method by trying to align all the eigenvalues, eigenvectors. It actually has this guarantee when it will succeed when average degree is polylog n, and the fraction of default edge is 1 over polylog n. So I think the big open problem for this method is that you get like a theoretical guarantee for this double stochastic relaxation of this QAP. Numerical experiments actually suggest that this can tolerate a constant like error. So delta can be a constant, but we're not able to prove that. So that's actually a big open problem. There's some other directions you might want to explore. Is there any way that we can go beyond even these like independent pairs assumption? Like for example, like geometric graphs. I think that's actually a harder, also a very hard question. And then here are the references. So the talk are mainly based on the last two references. Yeah, I think that's all I want to say. Yeah. Yes, go ahead.
So what is the resolvent machinery giving you? Is it enabling you to exploit this concentration for Gaussian in the bilinear form and things
Yes,
like that? So
yes.
basically the resolvent is putting all of these things in that bilinear form so that you can plug and play.
Yes, exactly, exactly. And then using this leave one out kind of technique. So then you can single out the like the first row or the first column with the rest of the submatrix. So then you can condition on that submatrix, and then use the concentration of the first row. And yeah, I mean that kind of technique is actually used very often. I mean it actually always comes together with this resolvent technique. Yes, so often if you do this, you want to use this resolvent, you also do this leave one out kind of techniques. For example, if I remember loosely, that's how people to show this convergence of empirical eigenvalue distribution. So they also use a similar technique.
The Wigner.
Yes, yeah, the Wigner semicircle.
Changes transform. So you're saying this resolvent.
Yeah.
Okay.
Yeah. Okay. Yeah. Yes.
Did you apply some estimation inside the interval, inside the quadratic?
Yes, I did apply. So, for example, like this is the plot that I skip, but you do apply the local loss to compute the trace of this.
So you actually
Yes.
and integrate along the contour that
Yeah.
the upper bound that you get.
Yes.
Okay.
Yeah, I did that. But here the crucial thing is that, as Siva mentioned, is this a bilinear form in the previous stage. So this is the crucial thing. So I single out this A1, B1. So that's why I can apply the concentration over A1, B1. And then this part I can just apply the local loss to approximate this and then compute the trace. The same thing for the off-diagonal entries. Yeah. Yeah, and then in fact, this resolvent technique is actually also used a lot in other contexts. Like if you want to get some refining information about the eigenvalues, eigenvectors, so this is actually the default method that people to use. Yeah, so if you encounter similar things in your other problems, maybe that's the useful tool to check. Yeah.
I saw it in the context of Markov chain mixing.
Oh, okay. Yeah. Yeah, and then in the next lecture, I'm going to talk about some other methods from the low-degree polynomials. So that's another very kind of common technique you can apply to many other problems. But that's, yeah, I want to say. Okay, so see you tomorrow.